Okay, all right. Now that you've all been through a whole day's worth of workshops, you've done lots and lots of things, your brains are really tired, we're going to give you the really serious stuff. Okay? So this is something where you're going to have to put your thinking caps on. And I apologize in advance to the elementary school teachers that a good amount of this talk will go right over your kids' heads. But this is professional development, okay, that you are going to, expand your professional development. I don't expect you to teach general relativity to your kids, although you can teach them the three-word summary, all right, which we will get to in a minute. All right, so we call it Space and Time Can Warp Your Mind, and it is going to show you some of the science background and expand your ideas of space and time. Because when we think of space, we often plot it as this grid work, this thing that sits in the background. With physics, who are the physics teachers here, right? The physics teachers here. We have this space that you go through, and it's the background to your calculations. All right, and then we have time, and time is actually pretty hard to define because we don't actually really think about it that much. It's always happening. As I put up here, the constant drumbeat existence, or I love this quote, time is what happens when nothing else does. Okay? And we can measure time really, really carefully. But the point is that the straw man that I'm throwing up here is that space and time are this background stuff in which the universe happens, in which things happen. This is the background. And I want to dissuade you of that notion today, okay? That they are not background players. They are actually involved in the game. So let's take it slowly. Let's start with space. And one of the best ways to express space is through looking at our cosmic address. Okay? This is something you can do with the elementary school kids. And they love it. They absolutely love this because it's thinking of where we exist in the universe. So if we wanted to write out our full cosmic address, well, we'd start with our house. All right? And I got to tell you, I just pulled all these pictures from lots of different places off the internet. I'm really not sure. I know this is somewhere in Pennsylvania, okay, and it's some historic house somewhere. But we have the house, okay? That's where you start your address. And your house is on a street, okay? And that street may be part of a neighborhood. I found a nice picture that included both a subdivision and a school and a ball field, and I don't know, we could pretend this is shopping or something, all right? You have your neighborhood around there, and that neighborhood may be just one small part of a much bigger city. This is, anyone recognize the city? Philadelphia. Okay. This is Philadelphia, 93.3 WMMR? Yeah, all right. All right, would this be Franklin Field here? I think it would be Franklin Field, okay? This would probably be University of Penn, University City in Philadelphia. Okay, so you got your house, your street, your neighborhood, your city. Cities are part of counties. This is Wake County in North Carolina, which contains the city of Raleigh, along with a few other municipalities. All right, your counties will then, of course, be part of your state. All right, and what state is this? Wisconsin. Okay, geography isn't totally dead in the United States. Actually, Denise is giving you the thumbs up because Denise is actually from you went to school in Wisconsin. Are you from Wisconsin?
I am from Wisconsin.
She is from Wisconsin. We have a cheesehead in the house. All right, and Wisconsin is one state in a country, this being the United States of America. And country is part of a continent of North America, and then our continent is one piece of our planet, on planet Earth. And hopefully, at this point, all of the addresses come together, okay? All the people get to planet Earth, except for those on the space shuttle, I guess. They're allowed to. They're a space station. They're allowed to say they're above planet Earth. But eventually, we'll get to planet Earth. Now we got to start on our astronomical address, okay? Planet Earth is one of the 4 rocky planets around the sun. Okay? The rocky planets are the inner part of the whole solar system, which include the rocky planets, the asteroid belt, the giant planets, Jupiter, Saturn, Uranus, and Neptune, and the Kuiper belt, along with another component that we don't visualize usually. It's called the Oort cloud, which is much, 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 much larger, and it's very inconvenient. Okay? The Oort cloud is it's just much too big to express things, and also we know of very few objects in there, like 0. But, you know, we know it's out there, and that's a different talk. We'll talk about that, okay? So we're in the solar system. Our solar system is part of the Milky Way galaxy, but where we are in the Milky Way galaxy is something called the Orion Spur. All right, so our sun is here. This pink blob here is the Orion Nebula, all right, in the direction of Orion, away from the center. The center of the galaxy is up here, all right, and this Orion Spur is a small, I don't know, it's not a spiral arm, it's just a subarm within the galaxy. And you can tell that when I pull back to the full image of the galaxy. Here we have the Orion Spur, and here are these major spiral arms. Now, this, of course, is not an image of the galaxy. It is a drawing of the galaxy by an astronomer named Robert Hurt at the Jet Propulsion Laboratory. And it is based upon scientific knowledge, but it is, of course, a visualization because we're down in the plane of the Milky Way. We can't get up out of it to have a view like this. All right? So actually, a lot of this, especially the stuff on the opposite side of the galactic center, is difficult for us to know exactly what's there. All right, some of this is extrapolation, but it's a very nice drawing. Our Milky Way is one of the 2 large galaxies in our local group. What's the other large galaxy? Andromeda. I showed it to you this morning, okay? So the Milky Way is one large galaxy. Andromeda is the other large galaxy. The third reasonable sized galaxy is the Triangulum galaxy, Messier 33. All the rest of the, say, 3 dozen other galaxies are dwarf galaxies. Small galaxies that are either hanging around the Milky Way or hanging around Andromeda or just floating out doing nothing going, dude, you know, we're just these small little dwarfs and we're just hanging out. Okay, but that is our local group, which is a pathetic nothing of a grouping of galaxies. All right, 3 dozen galaxies, of which 2 are worth speaking of, okay, because we are a nothing little grouping out on the source of a humongous grouping called the Virgo cluster. All right, that has 2,000 Sirius galaxies out in the Virgo cluster, along with the Ursa Major stuff and other groups of galaxies in the Fornax cluster. So really, we're in between Virgo on one side, Fornax on the other. Together, all of these groups and clusters of galaxies form what we call the Virgo supercluster. Supercluster, okay? We have a supercluster of galaxies out there, but it is not the only supercluster of galaxies in the universe. Virgo supercluster is just one amongst many of the other superclusters out there in the universe, each of these superclusters containing tens of thousands of galaxies. That's our cosmic address. Start with our house, street, neighborhood, city, county, state, country, continent, planet, in the rocky planets, in the solar system, in the Orion Spur, in the Milky Way galaxy, in the local group, in the Virgo supercluster, which is one tiny part of the entire universe. I did the exhibits at the American Museum of Natural History in New York, and basically we went through this on a scale, factors of 10, expansion scale, and basically one of our mottos was, if you don't come out of this exhibit feeling small, you really weren't paying any attention, okay? And since we were in New York, we actually put it more differently. If you come out of this with your ego intact, you really weren't reading. All right, so that is our place in space. Now let's think about our place in time. Oh, wait a minute. I want to also let you know that if you would like to do that and do it somewhat interactive, you can. There's a piece of free software that will allow you to do it. It is called Worldwide Telescope, and it is available at worldwidetelescope.org. It is a planetarium software from Microsoft. Now, I am not a Microsoft fanboy, okay? I really prefer using other operating systems besides Microsoft stuff. But this is a free piece of software from Microsoft Research that really, really does a great job of not only exploring the night sky, but also it has this 3D mode where you can start the solar system and pull back. Okay, it skips the local group, all right, because it doesn't have that stuff in there. But it allows you to do a 3-dimensional exploration of your place in the universe, as well as a lot of things on the night sky. I recommend it, and you can, there's lots and lots of features to it, okay? But then you can get that and do that in a sort of a powers of 10 like Zoom in software, okay? So now let's go on to time, all right? And we've had powers of 10, right? But I wanted to take that a little bit different direction and think about powers of time. All right, we think about what's the factor of 10 larger, what's factor of 10 longer in time? Well, let's think about it. Well, the first time periods that we all want to consider are the ones that come from astronomy. I'm an astronomer, and you know, we astronomers for most of history have been the timekeepers because it's the motion of the sun across the sky. That determines the length of the day. Right? You need us astronomers for that, right? Well, sort of. You can watch the sun yourself. We also have the motion of the stars at night. This is a time-lapse exposure of the stars orbiting around the celestial North Pole. All right? And you can see that this is Polaris. You can see it's not exactly at the North Pole, celestial North Pole. It's at 89.5 degrees north. All right? So it still makes things. And the length of this trail shows you how long this time exposure was. All right, but you can see that the stars orbit around. Actually, the Earth is turning. Right? Both the sun and the stars are relatively fixed, and it's the Earth turning in 24 hours. Going longer than that, we can watch the moon. The moon goes from full moon all the way back to full moon in how long? Anybody know? 27.3 days sidereal. By watching it, it's 29.3 days when we watch it from Earth. Okay, it actually takes 27.3 days to orbit, but because the Earth has moved a little bit during that orbit, it actually is 29.5 relative to the sun. So relative to the Earth is 27, relative to the sun is 29. Either way, this is how we define the month. Okay, astronomy defines the month. Astronomy also defines the year. If we figure out where the sun is on the sky and what stars are behind the sun, these are the stars of the zodiac, okay? Although they're missing Ophiuchus for some reason. There are 13 constellations that the sun goes through, not just the 12 of the zodiac, but also Ophiuchus. Oh well, we didn't actually expect astrology to tell us anything useful, did we? I certainly hope not. You can also track it by looking at the height of the sun. This is a wonderful picture called, it describes an analemma. And it is a picture of the sun at the same time on various days throughout the year. And you can see that it's up high. What season would it be? Say that louder. Summer. Thank you guys. Come on, you gotta work with me here. If it's down low, what time of year would it be? Winter. Thank you very much. Okay, going of course through the equinoxes and everything. Okay, so we can gauge the passage of the year. So that's how our motion of our planet determines our basic time units. The rotation of the Earth forming the day, the rotation of the moon giving us our month, and the orbit of the Earth around the sun giving us our year. So on human time scales, we live for years. We live for decades, okay? So we start out with years. This is a wonderful picture I found that has 4 generations. So we have child, mother, grandmother, and great-grandmother. All right, and this is sort of to remind us that if we're lucky, maybe we'll go many decades. We might even hit a whole century. Okay? I don't know. My relatives haven't lived to be 100 years old, but you know, maybe I can set the record for my relatives and my family history. All right, so we're getting up to decades and to hundreds of years. We know that, of course, our country is only 200 years old. The history here of us in the United States is only 200 years old. So what's thousands of years old? Well, there's plenty of examples of thousands of years old. One of my favorites is the pyramids. Okay? Pyramids date from ancient Egypt, thousands of years ago, like 5,000 years ago, for the pyramids like this. Okay? Now we'll think back, okay, let's go up another power of 10 to 10,000 years ago. Well, 10,000 years ago, this is the cave drawings in the Chauvet Cave in France. All right? Our early ancestors, these are dated to 30 to 32,000 years ago, drawings of what looked like buffalo and horses in the Chauvet Caves, 30,000 years. Let's go back another power of 10. We get to 160,000 years ago. These are 6 skulls that, or they may be, they look like they're 6 different ones, well, if I remember the caption for this, that relate to our earliest human ancestors, Homo sapiens ancestors. All right, there is some debate on these skulls here, whether they are a small sub-branch of Homo sapiens, but the modern humans have only been around for about 160 to 200,000 years. Okay? So we can go back in our family tree to other species, but Homo sapiens, we're talking 160,000 years. If we go back millions of years, we get to our ancestors. So here's Homo sapiens, and here's our family tree to Homo erectus, and so on back to Australopithecus afarensis. All right? This is the prime example of Australopithecus afarensis, which you probably know by a more familiar name, Lucy. Okay? This is the Lucy skeleton. Actually, it's probably a cast of the Lucy skeleton. Let's be honest, most of the museums, when you see the bones, they're not real bones anymore. They're actually casts. All right? But the Lucy skeleton does date from about 3.2 million years ago. All right, so we're getting pretty far out in time, out to millions of years. If we go back tens of millions of years, we get to the dinosaurs. This is T-Rex. This is a T-Rex in the Denver Museum of Nature and Science, all right, and is dated to about 67 million years ago. Something interesting I learned while preparing this talk is most of the T-Rex skeletons we have date from the very end of the Cretaceous period. All right? I didn't find any T-Rex skeletons that were 120 million years old or 80 million years old. They were all in the last like 5 million years of the Cretaceous. Now, I don't know if that means that T-Rexes only existed in the last few million years of the Cretaceous just before they got wiped out by the impact, or whether that's only the ones we found here in the US. But that was kind of cool. T-Rex, all right, at the end of the Cretaceous Tertiary, at the end of the Cretaceous period, 67 million years ago. Hundreds of millions of years ago, this is a trilobite from the Cambrian explosion. Okay? About 500, a little more than 500 million years ago, we had the greatest proliferation of life in the fossil record. Okay? Now this, of course, is only maybe a centimeter across. It's measured in millimeters in terms of this. This is a huge blow-up of it. Right? But at that time, the variety of life changed enormously around 500 million years ago. So now we start getting to billions of years, and then we get to the oldest rocks here on Earth. Now these are from Western Australia. They are rocks that are dated at 3.5 billion years ago. And I chose this image because in here there are striation patterns indicative of perhaps the earliest life. All right? The earliest life on Earth. We know they were there by 2.5 million years ago, but they may have been there 3.5 billion years ago. There is a lot of question as to whether this truly represents life 3.5 billion years ago, but most people sort of find that they seem to, I'm trying to gauge it as a scientist would, you know, with enough weasel words, that say they seem to indicate that there was life 3.5 billion years ago on here in life. Now, of course, going further, we can't go further back on Earth, simply because Earth is only 4.6 billion years ago. I can't go another power of 10 in time on Earth. And the sun itself was formed with Earth about a little bit earlier than Earth, about 4.7 billion years ago. So to go further, I've got to go actually outside of Earth and outside of our solar system to find something even older. I take the globular cluster Omega Centauri. Omega Centauri is a globular cluster of about 1 million stars. And one of the cool things is we look at these stars, they seem to indicate that these globular clusters, all the stars basically formed at once. Okay? They all formed together within a very short period of time. And in looking at that, we can gauge the age of the stars that are just now dying as being the age of the whole cluster. So we can actually age date this cluster to 12 billion years ago. And that's only 1.8 billion years after the Big Bang. So we're going out and looking at ages of things in the universe, and we're getting back to just a few billion years after the Big Bang. So that's our age in time. We live for decades, but we can trace our history in time out to 10 billion years. Long, long ranges. Long ranges in space, long ranges in time. Okay? Now, let's talk about how we would connect space and time. Okay? So here is an invitation to a wedding. And if you look through it, there's something missing. They request the presence at their marriage on the 17th of September at 4 o'clock in the afternoon. What's missing?
Location.
Sorry?
Location.
Location. It tells you when, but I've actually blocked out where. Okay? Likewise, here's an announcement of a public meeting at the Greenwood Community Center discussing the board's concern about the ongoing declining use of the branch. All right? And you are invited to the Greenwood Community Center. But what you don't know is, when is this meeting taking place? Oh, well, it's Wednesday, April 16th, because I blocked that out. I did this as a point for you to recognize that the two crucial points that you need in an invitation are where and when, right? You need to think about these things. You think about the reporter's questions. Who, what, when, where, why, and how. Okay? Where and when are your space-time coordinates. All right? We speak of in relativity space-time coordinates. Thinking of things in terms of space and time. Time is a fourth dimension. All right? It's not something crazy that only Einstein would think of. It's already part of your thinking. Where and when. If I make my Outlook appointment for doing some teacher workshops at Goddard, I have to say where it is and when it is, okay? Space-time, the point here is that space-time coordinates are not something foreign that only astrophysicists think of. It's part of your everyday life. Furthermore, not just only are the coordinates a part of your everyday life, you also know how to do space-time calculations. Okay? When we think of this, we think of the physics. Okay, that x1, y1, z1, t1, and then you're going to x2, y2, z2, t2, and we have to do the four-dimensional calculation to do the distance between those, right? Sounds like complex mathematics. The mathematicians guys here are going, yeah, I love it, right? Okay, and the rest of you are going, well, you know, do I really want to do those calculations? Yes, you do, and you can do them in your head. Matter of fact, the people who are best trained to do that, some of the people who are really best trained to do it are baseball players. Okay? This is a great image. This is a fantastic image because it captures that very specific moment in time when he's about to hit that baseball. Right? But what is this baseball player doing inside his head? He is doing space-time calculations. He has to be able to swing at the right time and at the right point in space to be able to hit that baseball. All right? And that baseball is curving, and the fastball pitcher is coming in at 97 miles an hour. All right? He swings too early, he misses it. He swings too late, it's in the catcher's bin already. He's doing space-time calculations in his head as his job. All right? Another one. Quarterbacks. What is this quarterback doing right here? He's looking downfield, trying to see his receiver, trying to figure out where in space-time do I need to put this football so I can complete the pass. Now, I don't want to insult football players, but most quarterbacks don't graduate in astrophysics with astrophysics degrees, okay? They're not the ones who are going to be doing space-time calculations in general relativity. But they are extremely good. Matter of fact, the ones who will make it to the NFL are extremely good at doing space-time calculations in their head. And it's not just professional athletes, it's everybody. Because how many of you drive? Okay? And when you are driving, you are constantly doing space-time calculations. All right? Have you ever tried to make a left turn across traffic? You're gauging the oncoming traffic. Can I make it before they're going to slam into me, right? You are doing space-time calculations. Have you ever tried to go into a roundabout, a traffic circle? All right, how many people don't like traffic circles? All right, do you like this? And why don't you like them? Huh? Yes, you don't know, and there's a lot of variables going on. When this guy here is entering this traffic circle, he's got to be watching the traffic, gauging where is there an opening in space-time for my car to fit into the traffic in the circle. So by this measure, the best people in the world at doing space-time calculations must be the French. Especially the French who live in Paris and have to drive around the Arc de Triomphe. Because if you've ever been there, there are like 12 different streets that go into this traffic circle. There are no lanes marked wherever in this traffic circle. You can just stand there and have fun watching the crazy traffic go all around. It's totally chaotic. Okay, so this shows you that the French might be the best at doing space-time calculations. All right, and if you do not do those space-time calculations correctly, this is why you are so good at it, there are serious consequences, right? So, space-time calculations, we all do them, whether we play sports, whether we drive or ride a bicycle or skateboard or whatever. We're all constantly doing space-time calculations. We have to do them well. If we do them well in sports, there are incredible rewards for that. Okay, you get paid pretty well if you can do them in your head. But there are also severe consequences in terms of crashes that might happen. Most importantly, I want you to recognize that you do these unconsciously. Okay, this isn't some calculation that you're doing, that you're trying to do mathematics in your head. Okay, you do the math in your head, but you do it unconsciously, and it's part of the way you do it. So let's not think about general relativity and special relativity as being this crazy stuff that nobody does. It really is part of your life. So let's connect space and time a little bit further. Okay, let's talk about how time warps our view of space. All right? This is one of my favorite images. Actually, the folks who hear me give these talks a lot go, yeah, Frank, you have so many favorite images. But this is one, because this is the first image ever of Earth and the moon in the same frame. It was taken by the Voyager satellite looking back on Earth to get the Earth and the moon in the same frame. This is home, folks. Okay? This is our home in the universe. But there's one thing I don't like about this image, in that it's foreshortened. The distance between Earth and the moon looks like we're cozy up next to one another. And that's not really the distance. The distance really is about 380,000 kilometers between Earth and the moon. All right, an easier way to memorize that it is 30 Earth diameters. The moon is approximately 30 Earth diameters away. And that's a pretty big distance. Matter of fact, it is such a big distance that it takes 1.2 seconds for the light to travel from Earth to the moon, or vice versa. Okay? And if you are my age, you actually have experience with that. Because if you ever listened to the Apollo missions, all right? And Kennedy Space Center would go, Eagle, we need an update. Yes, thank you, Eagle. Can you elaborate? Okay, I got that wrong. There was always that delay from when Kennedy spoke and then the astronauts replied. And it was at least a 2-second delay. And it wasn't because the astronauts were sitting there going, well, what should we say in response? And then figure out what to say. No, instead, it was that it took 1 second for the light to travel to the moon. Then the astronauts responded, and it took 1 second for their response to get back here to Earth. There is a built-in 2.5-second delay in any conversation between Houston and the moon. Okay? That's kind of cool, right? We have it in our folklore, proof of the light travel time to the moon. If we go further, we can talk about the light travel time to the sun. The sun is 150 million kilometers away. All right? The speed of light is 300,000 kilometers per second. Okay, 150 million divided by 300,000, easy math, 500. 500 seconds for the light from the sun to travel across the intervening space and reach us. Okay? The light that leaves the sun right now is not going to reach us for another 500 seconds. 8 minutes, 20 seconds from now, that light will finally reach us. That's kind of cool. We're seeing the sun as it was 8 minutes ago. If we go across the solar system to Neptune, we see even further into the past. We're seeing Neptune as it was 4 hours ago. It takes 4 hours for the light from Neptune to cross the 29 astronomical units of space before we see it here on Earth. Light from Neptune is at least 4 hours old. So let's see, it's 3:30 now. The light from Neptune came from 11:30 this morning before the soccer match even started. Okay? So the folks on Neptune have no idea about the USA-Germany game because on Neptune, they're still getting the information from Earth that is 4 hours old. Okay? They're still stuck before lunch. What were we doing before lunch? We were doing the Hubble Deep Field and the lensing activity. Okay? So if the folks on Neptune were studying our group, all they can see right now is us doing the lensing activity before lunch. Okay? The light from what we're talking about right now, this talk, won't get there until 7:30 tonight. Kind of cool. Let's go beyond. We got light hours across our solar system. If we want to get out to the nearest stars, it's much, much further. This is Alpha Centauri, one of the nearest stars, and Beta Centauri. But the nearest star is Alpha Centauri C, or also known as Proxima Centauri, a pathetic little nothing of a star here, which is this star right there. Proxima Centauri is 4.22 light years away, which means the light from Proxima Centauri has taken 4 years to get here. All right? Now, people often say that they want us to travel to the stars. We've gone to the moon, let's go beyond, let's get to the stars. All right, so everybody, let's hold our breath for 1.2 seconds. Ready? Okay, good. You've made it to the moon. All right, we want to make it to Proxima Centauri. All right, everybody, let's hold our breath for 4.2 years. That's the difference, okay? In making it to the moon in 1 second and making it to Alpha Centauri in 4.2 years, okay? That's the whole scale difference of the universe. And when you put it in a time factor, it's kind of powerful. We just put it in millions and trillions of miles, well, it's not quite as powerful sometimes. All right, so it takes 4 years to get to the nearest of stars. What about our island of stars? This is another drawing of the Milky Way. Again, we've got a bar in the center. The sun is in the spur in between two major spiral arms. All right, well, the sun here, to get to the center of the galaxy, it would take 25,000 years for light to travel to the center of our galaxy. Our sun is about 25,000 light years from the center, and across the whole galaxy is about 100,000 light years. Okay? Our galaxy is about 100,000 light years across. It takes 100,000 years for light. So, if you think about it, let's put that in translation. Our Homo sapiens, right? 160,000. The light from there would have traveled beyond our galaxy, just beyond our galaxy, about 160,000 light years out into space. But it will not have traveled outside our galaxy very far because the distance to our nearest big galaxy, okay, distance to the nearest big galaxy is 2.5 million light years. Okay? One of the dwarf galaxies is about 160,000 light years. They can see Homo sapiens on Earth. These guys, well, they don't see the Lucy skeleton. It's 2.5 million years, not 3.2. But they see one of the follow-ons to Lucy, Australopithecus africanus. Okay? When folks in Andromeda look at Earth, they see it as it was 2.5 million years ago, and vice versa. Let's go beyond Andromeda out to the Virgo cluster. This is the center of the Virgo cluster. These are the biggest galaxies at the core of the Virgo cluster. The Virgo cluster encompasses a huge region of the sky in the constellation of Virgo. Thank you very much. Come on, I give you free ones. You know, take advantage of them every now and then. All right, all these galaxies out there. The Virgo cluster extends from about 60 to 70 million light years away. So these guys in the center of the Virgo cluster, they look at Earth and they see T-Rex. Okay? The light left these guys, alternatively, at the same time T-Rex was alive on our planet. Tens of millions of light years out there. And if you go into the ultra deep field, as we discussed this morning, we're talking billions of light years out into space, billions of light years back into time. Time warps our view of space because as we look out into space, we're looking back into time. All right, we have a time-warped view of the universe. Here is a drawing. Oh, sorry, I got to introduce the concept, which gives us a finite universe. A finite observable universe. Now notice I use the phrase observable universe. It's very important. The whole universe may be infinite. Okay? Space may go on forever. But the part we can see is finite. Because there is a finite speed of light and there is a finite age of the universe, which means there's a finite volume that we can observe. Light from more distant regions hasn't had time in the entire history of the universe to make it to us. All right? If there are objects, if there are galaxies 16 billion light years out there, the light from them hasn't had time to make it to us, so we can't see them. Okay? We won't see them for another 2 or so billion years while that light continues to make it to us. All right? So, if we have this drawing that we did up at the Hayden Planetarium, we've got the Milky Way in the center, we've got the Magellanic Clouds here, here's Andromeda, I think over here is the Virgo cluster, down here is Fornax, and so on out to the edge of the universe. What is at the edge of the observable universe? Well, it's as far out in space as you can see, and it's also as far back in time as you can see. So the edge of our observable universe is the Big Bang. Okay? The beginning of time, space and time. So what we actually see, the most distant objects we see in the universe, is the cosmic microwave background. The radiation from 500,000 years after the Big Bang. As the universe was cooling and electrons combined with protons and light could finally free stream through the universe, the light from that earliest time in the universe is observable today in microwaves. So we can see out into the universe and back in time to about 500,000 years after the Big Bang. That's kind of cool. All right? So, let's go further. Let's talk about where things go beyond this. All right? How we've got space, we've got time, and our warped view of it, but motion actually warps our view of space and time. And here's where we're going to get into special relativity. Okay? But first, let's talk about just motion, okay? That we're changing our position in space and in time, all right? And that we are always going to be in motion, okay? The Earth's rotation at our latitude, we are rotating around the center of Earth. We're moving at about 1,300 kilometers per hour, okay? Then our Earth is orbiting around the sun. There we're moving about 100,000 kilometers per hour. Our sun, in turn, is moving around the center of the galaxy. It rotates around the galaxy in 250 million years, but it's still moving at 720,000 kilometers per hour. And then, relative to that microwave background, we can measure the motion of the Milky Way through the universe. It's headed towards the Virgo cluster at about 2 million kilometers per hour. So if you think your kids just can't sit still, here you have justification. They really can't sit still. Even when you are absolutely perfectly still, you're still moving at incredible velocities due to the rotation and orbits and motion of things around you. So everything is always in motion. But that motion does change our view of the universe. All right? I'm going to skip this for now. All right? Because we're talking about the speed of light. And we've mentioned that it is finite and 300,000 kilometers per second. But under special theory of relativity, the idea is that the speed of light is absolute. Nothing can go faster than the speed of light. And furthermore, that the physics is the same to all observers. That anybody in any reference frame will measure the speed of light to be the same. Okay? These two ideas, that the speed of light is an absolute and the physics is the same, produce some really strange things in terms of space and time. First of all, in non-relativistic motion, if you've got somebody who's walking inside a train, he's moving at 2 kilometers per hour. and the train itself is moving, say, at 30 kilometers per hour. We do what we call a Galilean transformation, add together the 2 plus the 30, you get a total of 32 kilometers per hour relative to the ground. Okay, that's how we normally think of motion, that they add together in the vectors, all right, for the math folks. All right, the problem is if you're trying to do relativistic motion, you can't do the same mathematics. All right, so for example, he's running really, really fast and he's moving at 1/10 the speed of light. And this train is really super turbocharged, and it's going at 95% of the speed of light. If you add those two together, you would get larger than the speed of light, and the special theory of relativity posits that nothing can go faster than the speed of light. So this means that you have to use different mathematics when you're moving at relativistic speeds. Okay? Different mathematics applies to preserve the absolute of the speed of light. So the relativistic sum for the math, because I know there's some math teachers in here, most of you don't care about the mathematics. I just want to let you know that there is mathematics to produce it, okay? And that is how we do it. The point is that there will be different mathematics when you're moving at relativistic velocities. And it's this different mathematics that produces these crazy ideas. First crazy idea, time stretches and shrinks, okay? Time dilation. Time appears to slow down when measured by a moving observer. Okay? An observer in motion measures a slower amount of time. Okay? Now we're going to do a little thought experiment just to illustrate that real quick. We're not going to give you the mathematics of it. The idea is that if we shine light to a mirror and the light and the mirror are in motion, well, the light is going to travel along this, hit the mirror, and then come back down. And you are going to measure that distance for the traveling of the light, and you're going to measure a time, and you're going to get the speed of light. All right, so you've measured the hypotenuse of this triangle, right? So you've measured a certain time. Now, imagine that instead of sitting on the ground watching this happen go past you, you are instead moving with the mirror. If you are moving with the mirror, all you are going to see is the light go up and come back. You're not going to measure the hypotenuse, you're going to measure just the long side of the triangle. You're going to measure a shorter distance, and then in order to calculate the same speed of light, you also will have to measure a shorter time. So a shorter time for the observer that's moving with the mirror. The moving observer measures a shorter time. That is the essence of time dilation. That time slows down when measured by a moving observer. The person on the ground watching this happen, he measures a longer time. The person traveling along with it measures a shorter time. Which is really cool, because that's the way we travel into the future. Time travel is possible, but it's one way, and it's into the future. So, a travel to Proxima Centauri at 99% of the speed of light would take 4.26 years as measured from Earthbound perspective. We would watch them travel across this Proxima Centauri. It would take 4.26 years to get there. But the pilot on the spaceship would actually have a time dilation by a factor of 7, and he would only experience 7.3 months. That's cool. All right? You can travel to the stars. I said that 4 years, hold your breath for 4 years. You would only experience 7 months on those 4 years. All right? It is one-way time travel to the future. You can't get back. Okay? When you slow down and everything and you synchronize clocks, hey, it's changed here on Earth. All right? That also leads to another effect called length contraction, or shrinking space, as I call it here. That because you're measuring different times, if you try to measure the distances as you're moving, you're going to measure shorter distances. So the length of an object appears shorter when measured by a moving observer, and its length in the direction of motion. Okay? So if that pilot swooped past a football stadium, instead of measuring a 100-yard long football field, he would only measure it to being 14 yards long, 1/7 as long as he otherwise would. Length contraction also occurs. Space and time are malleable when you get to these really high velocities. Okay, so we get to a relativistic diet tip. If you move fast, other people will think that you are thinner. Okay? Einstein didn't do things just for geeks. He actually said something that's valuable in your everyday life, too. All right, now we move on to general relativity and how mass warps our view of space and time. Okay, we discussed this some this morning. I'm just going to review it again. 3-word summary of general relativity. Mass warps space. Big thumbs up. Thank you. Okay? When we think of gravity, and Newton described gravity as a force that pulls on objects and holds them in their orbit. Here's the sun, here's the earth. The pull of the force of gravity keeps it in its motion, and it circumscribes an ellipse around the sun. Einstein reinterpreted gravity as geometry, in not the force, but a warping of space, a change in the fabric of space-time. So you think of it as space as being this rubber sheet here. This is an actual rubber sheet done in a physics department. Okay, and you've got the rubber sheet and you have the grid on it, and then you take a mass and you put it inside that rubber sheet, and you can see it forms a depression in that rubber sheet. It warps the fabric of space-time. Then imagine that you were taking a little BB and you're rolling that BB. Could you make a nice little orbit around that? Well, certainly if you tried to roll it past it, it would deflect. Okay, and if this were done perfectly, you could actually put a little BB on an orbit that would go around it. So that the orbit of Earth around the sun is not due to a force, but it's due to the curvature of space putting it on that orbit. Okay? It's traveling a straight line through curved space. Wow, dude. Yeah, that's kind of fun, all right? It's not a curved line through flat space. It's a straight line through curved space. All right? Fun stuff. All right, this is what leads to gravitational lensing, right? That warping of space. More mass, more warp space can act like a lens. And if a black hole visited Baltimore, you're standing on Federal Hill, you're looking at these buildings here, and then a Jupiter mass black hole suddenly appears, boom! You would get this kind of warping. This is a scientific visualization of it, of what the light would do. You'll notice the light from above comes underneath it, the light from the left goes around, it all warps around it, okay? I will note, however, that the masks in the foreground shouldn't be warped, but hey, I didn't feel like doing the Photoshop to pull those out instead, you know, so we do our best. This gets the point across, right? Because we need these familiar visualizations of gravitational lensing, or using wine glasses, as the high school folks discovered, in order to understand images like this. This is the galaxy cluster Abell 1689. Huge amount of mass. You can see these streaky things. If I zoom in on it, you can see all sorts of these streaky, archy things that are produced by the gravitational lensing. The extra mass in this cluster, this huge amount of mass, warping space, and the light from these galaxies becoming distorted as it travels through that warped space. So this acts very much like a lens in that the light from the distant galaxy comes through it, is deflected, and we can see the light here on Earth in this change. Very much exactly analogous to lensing, although these clusters tend to be very, very strangely shaped. They're not simple lenses. All right, and the final concept is time dilation is not just for special relativity only. Time dilation also occurs in general relativity, and it's difficult to explain, but I'm just going to give it to you straightforward, that the deeper you are in a gravitational field, the slower your clock runs. Okay? So if the closer you are to Earth's surface, the slower your clock will run. The higher you are away from the Earth's surface, the faster your clock will run. If you are up in the mountains on vacation, you say, wow, time's really flying. Well, time is passing faster for you when you're vacationing in the mountains. All right, it's imperceptible on human scales, but it actually can be measured. They have measured this by flying an atomic clock in a plane. They've taken two atomic clocks, synchronized them. All right, one of them goes into the plane, the other one stays on the ground. They take this one up, they fly it around at high speed for some time. And they come back and land, and they look at the difference between the clocks. Two effects going on. One, it is slower due to special relativity. Excuse me. Sorry, that's my son trying to get a hold of me. It is slower due to special relativity because you're moving at velocity, right? All right, as you move at a faster velocity, it slows down. But you get up out of the Earth's gravitational field, and therefore it runs a little faster. Accounting for both of them, they can find out. You could actually think of today's atomic clocks as the best altimeters out there because they can detect an altitude difference down to 1 yard. So when we were talking where and when you're trying to measure when, you also have to consider where you're trying to determine when. Did I confuse you enough there? The clock that is on the second floor of the building will run differently than the clock that's on the first floor of the building. How cool is that? What?
We can prove that in Scranton High. None of our clocks are that.
There you go, okay. Her high school, the clocks are never, but I'm not sure that the difference between first and second floor hits there. All right, so what I really want to get across to you guys today is that the warped view of the universe, this warped view of time and space, is not just some idea that's out there that you might want to consider, but it's actually part of a fundamental structure of the universe. Because space can stretch, space can shrink, space can warp. Time, space, well, I didn't cover this, the expansion of the universe, that space does expand. Time can speed up or slow down. If you look out into space, you can see the past. If you travel at relativistic speeds, you can travel into the future. All right? The behavior of space and time depends on motion, the amount of matter, time, and in the expansion of the universe, the amount of energy involved here. All right? Above all, space and time are not just a background framework. All right? For most of the things, yeah, we can consider them as background framework. But when you get into cosmology, you get into relativity, when you think about gravitational lensing, they are no longer a background framework to the events of the universe, but they are a participant in those events. And if you think about them deeply, space and time really can warp your mind. Thank you for your attention. Okay, by my clock, I have 4 minutes for questions. All right. If no questions, I can assign homework doing Christoffel symbols. Oh, yes, go ahead.
How many yards is that?
How many yards of pacing did I do?
No, 4 minutes.
4 minutes. I don't know. We'll work that out. There's a question back in the back of the room. Yes?
In the example of the astronaut flying at almost the speed of light to another galaxy, and you said it was 4 years for us and 7 months for him.
Yes.
Maybe I have a misunderstanding of this. So aren't they moving apart at relatively the same speed from each other?
Well, motion can be considered relative. How do we know the astronaut's in motion and the folks on Earth are standing still? Couldn't the astronaut be considered he's stationary and the Earth is just flying away from him, right?
Yes.
Yes, right. That's the standard question, okay? Trust me, that kind of question comes up all the time. The question is, who experiences the acceleration? Because changing reference frames is acceleration. And in order for that astronaut to speed up to 99% of the speed of light, he will have experienced an acceleration. So that changes, that's the difference between the two reference frames. Okay? But very good question. Okay, because I sort of skipped over the motion as relative thing because I didn't have enough time today. Other questions? Yes?
Okay, the cave paintings.
Cave paintings, 30,000 years ago.
Lucy.
Lucy.
Distant, or the age of the Earth, age of the Sun.
Yep.
Okay, what method are they using to determine it?
Okay. Basically, for the Lucy skeleton, most of those would be carbon dating, radioactive dating of the elements. Knowing that certain elements decay in very long times, and knowing the half-life. And if you know the time that, say, a rock was formed, okay, then the elemental abundances are frozen at the time that the rock forms. Okay, so if lava produces a rock and then it hardens, at that time the elemental abundances are frozen, and then you can check for, say, the amount of carbon-13 versus the amount of carbon-12 inside that rock, deep inside that rock, and that will tell you how much has decayed from one to the other. Okay? Planets. Well, it's basically age dating the rocks on the planets. We have an evolution. We have a stellar model for the evolution of stars and how they age over time and such, and we can get some of that. But the age dating of rocks on the moon it was 4.55 billion years ago previously, and I think they just upped it to 4.6 billion years ago, which also fixes the age of Earth. That was just a recent result that I didn't read carefully. Did anybody else read that carefully? The age dating of moon rocks just changed a little bit? Okay, all right. You guys don't read the same newspapers I do. In terms of that, and so basically trying also look for the age dating of the oldest things in the solar system. Our understanding of how the solar system forms is that the sun forms in the center, and it takes 100 million years or so for the rocky planets to form around them. It takes a little less, tens of millions of years for the giant planets to form. Okay?